Okay, sorry about that. Okay, so I was talking about the plasmon, so we can think that plasmon is very different to what is happening on the blood. Okay, so the electric field in our setup is radially symmetric, allowing us to excite only the N equal to 0 plasmon mode. So the experimental data shown in the previous slide correspond to the M is equal to 0 and N is equal to 1 mode of the plasmon. Okay, so let's come back to the experimental data again. So in the left figure, you can see that the amplitude of the reflector signal versus the frequency of the RF signal applied to the LC circuit for VDD minus 46 and for VDD minus 100. And you can see that for VDD minus 46 volts, we have 2 peaks, and the separation between separation of the 2 peaks is roughly 7 megahertz, from which we can determine the coupling strength G over 2 pi to be 3.5 megahertz. Since this is larger than both the loss rate of the LC circuit, kappa over 2 pi, 0.4 megahertz, and the ejaculation rate of the electron, gamma over 2 pi, 1.5 megahertz, we can conclude that this system has reached classical strong coupling level. Okay, so we are considering how this strong coupling between the plasmon and the photons to be used for quantum information. The coupling between the plasmon and the photon inside the resonator is strong, as I already showed you. Other measurements have shown that the coupling between the plasmon and the Rydberg state is also large. However, the direct coupling between the Rydberg state and the photon in the resonator is weak. So we are exploring whether it might be possible to enhance the coupling between the Rydberg state and the photon in the resonator by using a plasmon as an intermediary. Okay, so that was about the electron on helium. So let me explain what changes depending on the cryogenic substrate material now. So I'd like to talk about electrons on solid neon. So as mentioned earlier, if you use neon, we have some surface roughness, and so the permittivity is higher, so the electron is trapped closer to the surface. And what is more important is the qubit is already realized using the electrons on neon. And so it was done very recently by some US researchers, and they have measured that charge coherence time, it is orbital qubit, and charge coherence time is 50 microseconds, so which is very long for charge coherence time. Okay. So the disadvantage of solid neon is that due to the surface roughness, it is challenging to prepare uniform qubits for quantum computer. The advantage of the electron on solid neon is their long charge coherence time. So we can make use of this long charge coherence time. So having a long charge coherence time, we can have electrical coupling with other physical systems. And more importantly, the spin state is expected to have an even longer coherence time, so potentially reaching up to 1 second or longer. Okay, so the 2 points is that spin state has a very long coherence time, and thanks to a long charge coherence time, we can have electrical coupling with other type of qubits or other physical systems. So that is why we propose to realize a spin memory with electrons on neon for integration with other types of qubits. For example, in the case of superconducting qubit, we can have the coherent transfer of the qubit state between the superconducting qubit and the charged qubit, the orbital state of the electron of neon, via a microwave photon inside the superconducting resonator. So additionally, the charge state and the spin state can be coupled in introducing a magnetic field gradient. So in the end, we can realize the coherent transfer of the qubit state between the superconducting qubit and the spin state of the electron neon. So this is how we like to realize a spin memory for the superconducting qubit using the electron spin state on solid neon. So we started experiment aimed at achieving this goal. Since we plan to use the spin state, it is necessary to apply an external magnetic field in the end. But in principle, in general, the superconducting material is fragile to the magnetic field, but we need to overcome this problem. So we fabricated superconducting niobium titanium nitride nanowire resonator. So if you make very thin strip of the superconductor, and then we can avoid having a magnetic vortex inside the superconducting material, and then it becomes magnetic field resilient. So this is why we made a superconducting nanowire resonator. So after growing neon on the superconducting nanowire, we deposited electrons on the neon layer. And the electrons are emitted via fermionic emission from a filament. And then the resonator can send the electron deposited near the gap of the two ends of the nanowire resonator, because this is where the electric field becomes maximum. So this is our experimental data. So we are measuring the resonance frequency of the superconducting nanowire resonator. So by varying the voltage, the amplitude of the voltage pulse applied to the filament, we observe the shift in the resonance frequency of the superconducting nanowire, indicating that more and more electrons are deposited on the neon. So after depositing many electrons, we perform what is called pump probe measurement, which is known measurement for superconducting qubits. So the pump signal was varied from 6 to 12 gigahertz, and we have observed a relatively large resonance frequency shift when we use 11 gigahertz and 6.8 gigahertz as the pump signal frequency, indicating that there are electrons coupled to the resonator whose orbital energy corresponds to these frequencies. Okay, so to detect the spin state, we will place ferromagnet near the gap between the two an external magnetic field along the y direction. The ferromagnet become magnetized along the same direction and creating a magnetic field gradient that couple the spin state and the charge state. So thanks to this coupling, we can detect the spin state by measuring the microwave photon response in the superconducting resonator. Okay, so this is what we are trying to do that, and the summary of my talk. So we aim to realize the hybrid qubit of the Rydberg state and spin state using electrons or helium. And we experimentally measure the Rydberg transition of many electrons using an LC resonator. And we also observed an uncrossing due to the coupling between the plasmon of the electron or helium and photon in the LC target. And we also measure the electrons on neon using a superconducting nanowire resonator. I would like to thank all the people contributing to these works, and thank you for your attention.
All right, thanks a lot, Erika, for this very pedagogical explanation of floating electrons. We have time maybe for one question before we go to the next speaker. Anyone? Otherwise, yes.
So thanks for the really interesting talk. So this setting where you seem to have a lot of cases where you have two states that couple to an intermediate state but don't directly couple to each other. To me, this seems like an ideal setting for like STIRAP type protocols. Is that something you guys are looking into doing for the controls for this, or are you thinking different directions?
So could you say again?
Oh, I was just wondering, some of these setups where you have an intermediate state, and then you have the two states that don't directly couple to each other, but you want to. seems like kind of an ideal setting for using, styrap.
Style.
Yeah,
In ion trap.
yeah, but using the same idea in this setting, is that
Okay.
something you've looked into, or?
So I don't know if what we are trying to do is exactly the same as style, but I spent some time that if we can use the style method. So sorry, I don't remember the detail, but in the end I remember that somehow I concluded that we can build it, but okay, I think it was because so for us we have a derivative state, and then we have the free state for all the derivative states, and then yeah. So I don't remember. Yeah. So sorry, I cannot answer well, but okay, can we discuss it?
Oh, of course,
Yeah.
very interesting, thank you.
Yeah, thank you.
All right, thanks a lot, Erika. We can thank our speaker again.